Okay, so in section 1.2, we go over a definition of vector spaces. Now, this is a rather short section, and we mostly go over definitions. The theorems we do go over have fairly simple proofs, so that should be fun. With that said, we'll start with an addition on a set V. So it says, the definition says, an addition on a set V is a function that assigns an element u plus v in V to each pair of elements u, v, in V. Right? And this kind of comes hand in hand with the definition of scalar multiplication. So scalar multiplication on a set V is a function that assigns an element lambda times v in V to each lambda in F and each v in big V. Right, so maybe you've seen addition and scalar multiplication before in abstract algebra, but it's really useful, and I mean it's part of the big definitions when we're dealing with vector spaces, which here u plus v, it's kind of just saying, okay, if we have u plus v, that's what is it got assigned, right? That was the addition of u and v in V. And notice how this is also in V. Scalar multiplication is if we have v in big V, say this was a vector space, even though we haven't defined it properly, we can scale that vector times lambda. So lambda here, notice how it says lambda is an element of F. That means it's a field. Maybe it's a real number, maybe it's a complex number. For this class, maybe it's something else from another field, but in this case we're dealing with real and complex numbers. So you scale that vector v. That's all these are. But now we move on to define the important definition, probably the most important definition in a while, which is a definition of a vector space. So a vector space is a set V along with an addition on V. So that's why we needed to define addition up here on V, and a scalar multiplication on V. And with these two definitions, the following properties must hold for it to be a vector space. First one is commutativity, right? So u plus v is the same thing as v plus u for all elements uv in V. They have to be associative. So here's associativity with addition, over here it's with multiplication. For all of these, u, v, and w in V. And here, a and b are elements of F, not V. So careful with that. Something else is the additive identity. So for every V, for every vector, I suppose in the vector space V, there exists a W, a vector W, such that if you add those two, we get 0. We have multiplicative identity, which is 1 times a vector is just a vector for all vectors in V. And finally, our last one is our distributive property. Now here, before you even read these, to not get confused, before you read those two, to not get confused, note first that A, B are in F. So they're real or complex numbers, and U, V are vectors. Right, so here we're distributing an element of the field F, right, which gives us this. Over here, we're distributing a vector, which gives us this. So just careful with that. Make sure to note that. But if these properties hold, then we have a vector space. Okay. Next up is elements just the definition of vectors. Elements of a vector space are just called vectors, or you can call them points as well. And here's just a little illustration. We have a blue vector there, red vector over here, and a green one over here. So this forms, these are three vectors, and we're going to talk about other definitions that are yet to come, like span or R3. Even though we've already gone over R3, but we know this is R3, there's a cube forming there. But to not confuse, we're just going to go ahead and move on. And here's something we should not just note, but something to have in mind. That's why the box is yellow. So the scalar multiplication in a vector space depends on f. So over here, at the top, notice how at this definition, lambda is in f, right? So when we do need to be precise, we need to say the vector space is V, sure, but it's over f because our scalars are in f. We say that to be precise instead of just saying, oh, V is a vector space. Okay. And finally, the probably definition you already knew is a vector space over R, where the scalars are in R, is called a real vector space. And a vector space over C is called a complex vector space, where the lambdas are in R and the other one are in C. That's the real and the complex vector space. Okay, moving on, we go to our example of vector spaces. So I have a question. There is what's really known as a simplest vector, which only contains one point. Can you try to guess what it is? The vector space is the element 0. Careful, it's not the empty set. This is the 0 vector. Okay. Something more interesting is we have f infinity. So f infinity is defined to be the set of all sequences, as you can see here, x1, x2, so on and so forth, for, well, just infinity. Now here, if we define addition and scalar multiplication on f to be defined, well, as expected, as we had defined before, the vector addition and scalar multiplication. So like this and like this, as you can see here, this actually forms a vector space over f, of course. I forgot to say that. Over f, right? Where lambda is in f. So this actually forms a vector space over f. Now we do need to check that all the properties hold for the vector space that we mentioned on the last slide. We need to make sure those hold. So I'm going to include a little animation here where the guy doesn't know if it's a vector space or not yet. So here I'll include vector space. That's something we need to do, and maybe your professor will give you an exercise to verify certain if something's a vector space or if it isn't. So moving on, something about notation is if set S is a set, then f to the s, what that looks like, f to the s, actually denotes the set of functions from s to f. Right, so functions from s to f. For f and functions fg in fs, the sum, we define that as this. So you probably already know or remember this from high school. But f plus g of x is the same thing as f of x plus g of x for all x in S. And something else is for lambda in f and f in fs, the product we define as follows. We have lambda f time of x. We can take that out, that lambda out. and we have lambda times f of x for all x in f. And this is going to come up a little later. So I don't have too much to say about that right now. Okay, now, if we have S as a non-empty set, then Fs is a vector space over F. Again, it's things we can verify, but I can tell you that the additive identity is a zero function defined by 0 of x is equal to 0 for all x in S. And the additive inverse for function f in Fs is just negative f, right? And it's defined as following, as it says here, for all x in S. Something I want to mention about Fs is, so here it says it's a set of functions from S to F. Can you think of examples of f of s that we've seen before? An example can be Fn, right? We saw that in the last lecture. And what that is basically just saying f from 1, 2, so on and so forth, all the way to n, right? Because S is a set. Here we have the set. And for short, we just write n. The other example I'm going to write in blue is f infinity. In this case, infinity is our S. And here, if we are to write it out, it would be again something like this. 1, 2, but this one just goes on and on. Those are both examples of Fs over here that we see. Okay, moving on to actually the last slide. I have this little illustration. And the reason I have this little illustration is because there's only one yellow smiley face in a bunch of blue ones. Because the theorems that are up next are, I'm just going to put both of them up. One says a vector space has a unique additive identity. And the other one says every element in a vector space has a unique additive inverse. So that's what I was kind of going for. That they both mention the uniqueness. That's why that little illustration. But a vector space has a unique additive identity. And these, again, are really easy proofs. They're pretty straightforward. You can even see the little box. To prove that there's a unique additive identity in a vector space, we're going to suppose 0 and 0 prime are both additive identities for some vector space V. Right, so the way we show something's unique is get two of them and show that they're actually the same one. So if 0 prime is additive identity, well then adding it to this element, to 0, should not change this element, right? There's 0. And again, addition is commutative, so we can just rewrite it like this. And because it doesn't change that 0, well, it's just 0. And indeed, it shows that 0 prime is equal to 0. Right, so just one more time, 0 prime, you added to 0, and since 0 prime is an additive identity by our hypothesis, it doesn't change the 0, right? So the 0 over here remains unchanged. So that shows that they're both equal, and well, there shows that the additive identity is in fact unique. The proof is similar for this theorem to the right, saying every element in a vector space has a unique additive inverse. So how do we start with this? We suppose V is a vector space, and we're going to let V be an element of big V. So again, To show uniqueness, we're going to suppose W and W prime are additive inverses of V. Right? We want to get to our conclusion that W is indeed equal to W prime, which is the additive identity of V. Okay, so if W is an additive identity, we're going to just add 0 to it. The reason we add 0 is because, well, it's the same thing as W. But now 0 is the same thing as V plus W prime. Why is that? Well, because W prime, by hypothesis, we are supposing that it's the additive inverse of V. So they should, when you add them up, they should equal 0. So we're still equal to just W. And then we're going to use the associative property. Right, so now W plus V, and then outside is plus W prime. And we're also assuming that W is the additive inverse of V. So what should this equal in the parentheses? Well, because they're additive inverses, they should equal 0. Right, so we get 0 plus W prime, which is equal just to W prime. Which shows that W is equal to W prime. So indeed, there is only one additive, there's only one unique inverse, a unique additive inverse. Okay, what follows is I'm going to show a picture again, but now it's a 0. Right, so what do you think that has to do with? Well, with multiplication of 0. So again, the two theorems. So this one, I should note, this one on the left is telling us that the number 0 times a vector. This one on the right is a number, in this case a, times the vector 0. So now, to read the theorems, the first one is 0 times v. The number 0 times the vector v is equal to 0 for every vector in v. The one on the left says any number a times a 0 vector is a 0 vector for every a in our field. So our proofs, again, really straightforward. For v and v, we have that 0 times v. Well, 0, we can just put it as 0 plus 0, right? Because, well, 0 plus 0 is still 0. So afterwards, we use the distributive property. So now we have 0v plus 0v. And notice how 0v here is equal to, over here, 0v plus 0v. So the reason this proves it is because, well, 0v is already equal to 0v. So that means that this over here should equal 0. And that proves it. Right now, the one on the left, we just have a scalar a, and we multiply times the 0 vector. Again, 0, the 0 vector we just write as 0 plus 0, the vectors. Use the distributive property. And again, this implies that a0 is just equal to 0. If it weren't equal to 0, then a times 0 plus a times 0 equal to a times 0 would be a contradiction. And finally, we have one last proof that says -1 times v is equal to -v for every v in our vector space. So again, the proof is straightforward. For the vector v and v, we have v plus -1 times v. And here we just basically have a 1, which we write out over here. Okay, so that equals, using again the distributive property, we have 1 plus -1, which we know is 0. So 0v, which is equal to 0. And that should conclude our lecture for a definition of vector spaces.